All right. Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mikey.
This is Sahil. Welcome everybody to another exciting episode of Quirkcast. Before we all get started, the usual spiel about logistics. Post any questions or comments you have on the YouTube channel, and we'll get to them during the episode. So, all right, let's get into it. So Tim, I was watching a video on a couple of popular YouTube channels, science YouTube channels like Veritasium and whatnot. I was talking a lot about how gravity is not really a force, but an illusion, that it's like the bending of space-time. So I'm curious from your perspective, like, why has this suddenly come about? Because I learned in high school physics that gravity was a force. So yeah.
Yeah, and indeed, I also watched through some of those videos, and it looks like, and they're not entirely incorrect. Let's put it that way. But the main point they're pushing is sort of this one very particular viewpoint, and this is Einstein's sort of original viewpoint. Okay, so to start our discussion, let's go through what that is, right? So this is the content of Einstein's theory of relativity. Basically, Einstein sort of concoct a thought experiment that he imagined two people, one on a spaceship, uh, one on a spaceship, and that person, let's say Sahil, is blasted into space, very far away in deep space, way away from Earth or any massive bodies, and after a while he just kind of hang out in space, right? So this is Sahil, and the other person is you imagine Tim, for example, and Tim is just hanging out maybe in a really tall building in San Francisco in an elevator, and unfortunately the elevator malfunctioned, and it just kind of like, and the elevator malfunctions, and it just like falling in uh, it just kind of going down, and you can kind of remember this feeling as the elevator goes down. You feel like this, like whoa, it's sort of this weightlessness feeling, right? So the idea, and Einstein thought about this, and he thinks that, look, imagine Tim in an elevator versus Sahil in a spacecraft in outer space, right? And if you go through the math, you realize that these two people, they feel exactly the same thing. This feeling of like, oh, the elevator goes down, you feel this kind of like weightlessness, versus being in outer space, you're not near Earth or anything, kind of feeling this, like imagine like an astronaut feeling weightlessness. So Einstein proposed that in these two situations, because it's indistinguishable, there's no way for you to distinguish it. The physics behind them must be the same, right? And because in one scenario, for example, in the spaceship scenario, there's really nothing affecting Sahil in the spaceship, so you can't really say there's a force. So because of that, and of course, when the elevator is falling down, I'm actually feeling, you can, if you think of it in a high school physics level, I'm kind of feeling gravity falling down, right? But then this scenario, it feels like it feels like I'm feeling a force, right? So Einstein's conclusion is this: given two scenario, one clearly does not have a force, and the other scenario clearly has a force. Given that these two scenario is exactly the same, it must mean that gravitational force in the case of the elevator must be kind of like an illusion, like it doesn't really exist. It's not. It's the same thing as if you're in space not feeling anything. And this is where this idea is born, that somehow, because of this equivalence principle, people think that maybe gravity is not as legitimate of a force as we think it may be, right?
Huh. So so you're saying, so just to summarize what you're saying, if I imagine I'm in an elevator and it like, the ropes got cut and I'm free falling, versus I'm in space just mad chilling with no planetary bodies around or any really gravitational waves around, then effectively they're both the same thing, because in the elevator I won't be able to tell that there's any force because I'm free falling, versus in space I'm just hanging out with no forces acting on me. So in that sense, they're both equivalent to each other.
Yes. That's the content of the equivalence principle, and eventually Einstein used this principle to build the general theory of relativity. But this is the idea where the idea is born. That somehow it seems like gravity is not a force; it's like a fictitious force. Maybe it's fake, basically.
Can
Yeah.
I, like, so do you guys, have you seen those science fiction movies like Interstellar, where they try to simulate gravity by having like a spinning like toilet paper roll type object, and so you're like sticking to the sides, and that simulates gravity? Would you agree with would you say I'm correct in hypothesizing that another way to state the equivalence principle is that there's no way you could tell the difference between that and gravity?
Yeah, I think to some extent that's sort of the idea of the equivalence principle, right? Like you can't tell those apart. So the physics equation has to also, to some extent, accommodate that, right? Like there shouldn't be two different equations describing the same thing, basically.
So what are like I guess the limitations of that interpretation, or like why doesn't this story just end there? So that sounds very reasonable.
Yeah, I would say, I mean, the equivalence principle is a great principle. It's been tested to great accuracy, and personally, I believe it's probably true. But I think it's a little much, just based on that. We claim that a force is fictitious.
Well, yeah. Well, let's think about what the equivalence principle is saying, right? It's saying that if you're like accelerating in a car, that push you feel is equivalent to the push you feel from a gravitational force. And so people use this, as Tim said, to say maybe gravity is not a real force, since you can simulate it just by accelerating yourself in some way. But the reason why the equivalence principle holds is something we've talked about earlier. It's the fact that gravity is universal, right? It affects every single particle in our body in the same way. Unlike the electric charge, where you can have repulsive or attractive interactions, gravity just pulls on everything the same way. And so that's why when you accelerate quickly, you feel that push in every single particle of your body in the same way you feel the gravitational force in every single part of your body. So I don't know, like it's very confusing to me that people use this as a means to say that gravity is not a force. It's really it's the most universal force.
Yeah. I suppose this concept is born because people have this idea that if you don't feel anything, maybe to some extent a force doesn't exist. So there's sort of this concept that maybe a force could be turned on and off, right? And if a situation where there's a force, you can also always kind of describe it physically as a situation where there is no force, then people kind of tend to think that, hey, maybe the force was never there to begin with. But of course, I think this perspective is a bit naive. Like a force, in a modern understanding, it's not like this on and off switch, right? It's not like, hey, you turn on gravity, turn off gravity, right? A force is just, if our listener listen to our previous episode, we'll summarize it real quick here, right? A force in the modern particle physics point of view is just a particular field, a particular energy field that has a particular type of universal interaction to some extent that can tug and pull particles and make changes to particles, right? So in that interpretation, there's really no way. There's not really a way to kind of turn on and off the switch of a force. A force is just kind of there. It's just part of the property of the space-time. So I would say, if you think a force can be turned on and off, then maybe you can kind of think that, hey, maybe gravity is sort of something that can, that you can think of as permanently turned off in some ways. But
that's crazy. Who thinks of a force that way?
Yeah, it's almost like the high school level thinking of a force, right?
But that's terrible. The high school level, yeah. Yeah, I mean, I'm convinced that like all of this confusion stems from this idea that people have that like something called a fictitious force exists. So in high school, we learned like, oh, there's like fictitious forces. Like if you remember, like centrifugal force is supposed to be a fictitious force because it doesn't really
Coriolis
exist.
force.
Yeah, all that stuff. I don't like even without going to a particle physics definition. What is the definition of a force? A force is something that changes the trajectory of an object, more specifically changing its momentum. So you can change its trajectory or its velocity with respect to some frame. But a force is anything that does that. And so I don't know, like I have a PhD in physics, and I don't think there's such a thing as a fictitious force, but I'm sure most high school physics teachers would disagree with that.
So we have an audience question that I want to ask is at a high level, is the framework for thinking about forces always in relation to an object the force are acting on versus an outside observer making an assessment of what's acting on an object?
But sorry, what's the difference between those two things? Because an outside observer could be looking at the forces acting between two objects. How is that different from having force be like referential between objects?
I guess like one is where you think of an observer outside. I'm interpreting the question here. We probably think of an observer outside looking upon everything, seeing all the particles move and like, oh, this particle changed that direction. Must be something acting upon it. Versus we're like in the system and you observe relative to you, something is changing direction from your reference frame.
So which reference frame are we talking? Yeah.
I that's my interpretation of the question.
No, that makes sense. Yeah. Can force be defined completely relatively, or does there need to be like a quote unquote God reference frame to define it? That sounds kind of like.
I think Einstein's theory kind of tells you a solution to that, right? Like obviously the effects of something depends on your reference frame. Like this is sort of the effect of the Coriolis force, right? If you're spinning yourself around, it feels like the world's moving around plus some fictitious force, right? But your reference frame is no less valid than any other reference frame. And Einstein's theory, I think if there's a takeaway message from Einstein's theory of relativity is that you take any reference frame, your statement about the world is as valid as any other, basically. It's a language to translate what you see in one frame versus another. And I think the concept of a force really should be thought of as this more generalized way. It's completely reference frame independent. Sure, the effects might depend on how you view it, but there's sort of this abstract geometric concept.
The explanation for the effects might depend on it. The effects themselves won't.
Yeah, like I think there's an underlying structure that's beyond that goes beyond your reference frame, that tells you there's a universal language that tells you how particles interact with one another. That's what a force is, right? Whether you're spinning around, moving near the speed of light relative to some other frame, as long as you use the right language, the right translation, you will come to the same answer, using those calculational tools. I think that's the takeaway from Einstein.
Yeah, so I guess to redirect that to the audience question, force can be defined entirely relatively with respect to a certain point. And it can also be defined with respect to some observer on the outside looking at all these objects. And it's almost like there's like a physics theorem that says that if you take these two radically different pictures, there can't be any contradictions between the two.
Yeah, I guess I would think of it. Yeah, my viewpoint would be that Einstein tells you that if you believe in Einstein's theory of relativity, I think the answer is not that it's not that there's some absolute idea of something being right, something being wrong. I would say that it tells you that there could be multiple viewpoints to the same system, and then they're both correct, right? It's not like somehow one viewpoint invalidates the other one. That's what I would say.
It's very progressive.
Yeah,
in a way.
It's not like just because one viewpoint it says there's no force, does not mean that the force does not exist, right? That's the whole point, So ultimately, yeah, sure. Einstein's equivalence principle tells you that every time you're influenced by gravity, let's say you're falling in an elevator or whatever, you can always change it to a frame, like a locally inertial frame, in such a way that the force is gone. Basically, it's as if you're weightless, right? You can always do that. You can always rotate the force away, basically, but that doesn't mean that there is no force, right? I don't know if that makes sense.
You can only rotate it away locally in your environment.
Yeah, you can only shift the force away in one instance, right?
Oh, maybe that's what the audience, an outside observer looking in, will still see it.
Mm-hmm. Is this almost equivalent to, or at least same spirit of argument as talking about particles that are massless move at the speed of light, where if you could like rotate in everybody's reference frame, the force went away, then it doesn't truly exist? Is that?
It's kind of analogous, yeah, like in the sense that if you could catch up to a particle moving at the speed of light, then nothing would be, everything would be frozen. Is that analogous?
Because you're telling me that in my local reference frame, from my perspective, I can just simply transform my reference frame accordingly, and gravity no longer exists. But in your reference frame, it will still exist. For me watching you, it'll still exist where you are.
Yes, and Tim, is it true that like a third-person observer looking at in a simplified environment, just like me and the thing acting on me, then that person would be able to detect a force too? So
yeah.
It's only my, like, I can convince myself just in my own little box that this is not a gravitational force, and I'm actually in a elevator accelerating.
Yeah, like I think a good analogy is sort of like so Einstein basically turned forces into geometry. So you see a lot of these pictures, the rubber sheet, things being curved around, and you kind of and he interprets falling objects as just kind of following what they call the geodesic. It's just kind of their predestined path, almost, kind of, right? So the idea is that the world is kind of like a really curvy thing, right? You look at the grand universe, basically. There are curves everywhere, right? And the reason why objects fall is because if you draw a straight line on a curved surface, like a straight line doesn't really exist, it's forced to curve, so objects kind of move around, right? And when we describe, you can always kind of remove the force locally, meaning that if you zoom into this curved surface, if you zoom in small enough, you can always draw you can always draw your direction, up, down, left, right, front, back, and when you zoom in close enough, it looks like it will look flat, basically, right? But then we don't think of the force being zero as a global property, right? We think of when we talk about forces, we talk about sort of the whole geometry, right? Sure, like the force might be zero here, but doesn't mean that the force is zero everywhere. So
I actually think that's a different argument too, though, right? Even though they come from the same idea, but I guess like this geometry argument Tim is talking about, right? Like the idea is that if you take two objects and there's no forces on them, if they start out going in parallel lines, they'll continue going in parallel lines. What actually happens if you see like a planet and an object, the object curves and crashes into the planet. And so, classical relativists would say, okay, that's not really a force. Its space is curved in a way that it's guiding this rock that thinks it's going straight. It's guiding it into this curved path into the planet. So it's not really a force. But the point is, I would define a force as anything which changes that trajectory, right? So the fact that the geometry is responsible for changing that trajectory doesn't take away from the fact that it's a force.
Yeah, I would even that anything that has the capability of changing the trajectory, right? Like even if one instance it doesn't change it, as long as it has that capability, it's a force. I mean, it's like, and let me just add in the same vein, just you can go through every single force that we have. Ignore gravity, electromagnetism, the strong force, the weak force, and if you look at it, and in fact, you can apply a very similar geometric argument, if you go dig through the math a little deeper, so the strength of electromagnetic force, you can attribute that to the curvature of sort of this extra electromagnetic direction. It's very geometrical. So just like when an electrician, let's say, deal with electricity, the the amount of electricity you get hit with does not depend on the absolute voltage, right? Like when you see, hey, 120 volts, you get zapped. You actually won't get zapped if you are also sitting at 120 volt. Like a bird landing on a power line does not get zapped until the bird touches the ground, right? This is sort of tantamount to kind of, this argument in relativity, right? Electromagnetism is also relative to some extent. It only acts upon the difference in the electromagnetic potential. And if you go through the similar argument, you see that it's also very geometrical. You can also interpret it in that way. There's some abstract rubber sheet somewhere that's curved, and the reason why things have electricity, like charges repels, opposite charges attract, is also in a very similar geometric vein. They're really just guiding, hanging along on some geodesic path, some curved lines that they're predestined to follow. So it's very similar. I would say that forces in general and gravity, they're very similar to one another, right?
And it's weird because right after people discovered evidence that gravity might be a little different, they also discovered evidence that the other forces are very similar.
Wait, so wait, are you saying there's like a similar geometric interpretation to the other forces, not just gravity itself?
That is what he said.
Yeah,
Got
absolutely.
Got it. Huh. How would you explain about like strong and weak force? Because those seem like really just. Is there an easy way to do it, or if it's too difficult, we can move on?
There's two ways to do it, right? There's the way that Tim tried, but that gets hard for those forces. But then there's another way, right?
Yeah, it gets hard. I mean, the strong force, they're like 8 different colors, so you can think of them as.
No, that's. There's a box in the Peskin textbook that explains that, right? Like how color gives rise to attractive and repulsive forces. But
yeah, if you have really
there's an easier way, which is just duality, right?
Yeah.
Well, so is there an equivalence principle for electromagnetism, strong and weak force?
There is, yeah, and I think
Weaker.
I think that arise. So the equivalence principle, I think it comes down to this. It comes down to the fact that gravity is universal. I think you can massage the math in some ways. The equivalent principle essentially says that gravity is completely universal. You cannot dodge it. You cannot hide from it, right? And the analogous thing for electromagnetism is that electromagnetism is universal to those that feels it, right? So basically it tells you that an electron has the -1 charge, and if you have another particle that also has the -1 charge, they feel the same electromagnetism. Like that's the equivalent principle for electromagnetism. It exists.
It's nothing more than the statement that everything happens to have the same gravitational charge.
Yeah, pretty much.
Okay. My other question is like, does this hold also on like it should also hold on a particle physics level? Going back to the equivalence principle described in gravity, if you translate that into particle physics, like how would that translate? Just that everything has mass, or how would you think about that? Because it's not like you can put a particle in an elevator and have it drop. It's going to be all over the place. It's not like you can use general relativity to go to particle physics, because what does it mean to be in the reference frame of like a quantum mechanical particle?
You can still define a reference frame, right? Wait, does that become murky?
I mean, you can still do it, right? Like people have tested. I think people have tested equivalence principle at the particle. Well, actually, I don't think so. They haven't tested it, but
it would be hard. It would be like one of those Austrian guys like Zeilinger doing his little like precision quantum mechanics experiments. He might have done it.
Yeah, I hesitate to say they might have done it for protons and
that's an engineering limitation. I'm sure quantum computing scientists will be the first to really test that, right?
Well, no,
having absolute control.
I think they have tested to see if protons and antiprotons fall in the same way.
Oh,
and so far they do. I mean, kind of as expected, and that's kind of like a sort of like a test in equivalence principle. Like, as long as you have the same mass, you should feel the same thing, just like, in electromagnetism. If you have the same charge, you got to feel the same thing.
Wait, the most, I know the most precise test of the equivalence principle comes from the University of Washington and their pendulum experiment, right?
That I'm not familiar with.
Oh, I forget what it's called. It was cool. I used to know about it, but yeah, they have a little pendulum experiment that's like designed to precisely tell if there's a difference between an accelerating object and a gravitational object, and it's like a Rubik's cube of intellectual engineering, but for the life of me, I can't remember how it works.
Yeah. So I guess so your perspective is that both hold, where it's not necessarily that it's not a force, but it also has it's a force and it has a geometric interpretation to it. It's not like, let's throw out the force interpretation and only have the geometric interpretation and forget that it's a force.
Yeah, but he's also saying that all forces do have at least a similar geometric interpretation. So any kind of geometric argument you'd use to say gravity's not a force would apply to the other ones as well.
I see.
Yeah.
I see.
I would say it's one of those scenarios. I think it's silly to categorize something as a force or not. It's sort of in the same vein as, in quantum physics, like, is it a particle, is it a wave? Like why do we ask this question? As long as the math and the results turns out right, you can interpret it either way. So I think it's like this. Is a force geometry, or is it like some discrete force? I think it's both, right? Like in a particle physics language, a force is a force. It's a unit of interaction. Gravity satisfies that perfectly, right? It's a unit of interactions. Two particles can come in, interact. They can kick each other by exchanging a graviton, and comes back out, just like how two particles can come in, exchange some kind of photon, and get a kick out of it, right? We even measure gravitational waves. Gravity is a real force. I think case closed.
And in fact, the only thing special about it is the fact that it is universal. And so if being a universal force is disqualifying as a force, then I don't know what world we live in.
Have you guys seen the interpretation where if I'm like standing on the floor, it's not that I'm moving, but it's that the floor is accelerating me up at 9.8 meters per second squared?
That sounds like some normal force weirdness.
Yeah.
Yeah, I mean, if you like viewpoints like that, totally fine. Like, I have nothing against it. I mean, your math might get really messy if you think of everything as accelerating up. But if you do proper physics, you still get the right answer. I guarantee.
Yeah, the fundamental crux of Einstein's theory is that it doesn't matter which one you assume. If you do it right, there won't be any contradictions.
Yeah, and I would say even in modern physics, this goes beyond, right? Like in recent years, we actually have mathematical construction that tells you that regular forces, which are called gauge theories, to not be so technical, and gravity, right? Even though there's some differences, they are actually one and the same thing. They're actually multiple descriptions to describe each other. So, like for example, gravity can be described in some situation by a regular force like electromagnetism, and vice versa. Electromagnetism and strong forces and whatnot can be described by a gravity in a particular way. So this makes it even more concrete, like if you really ask me, like, what do you think, Tim? Like, where would you place your bet? I would tell you that gravity and all these forces, they are one and the same thing.
Mathematically, at least, yeah. Which, as far as I'm concerned, means absolutely.
So we're running up on the end of this. So I guess like we should end with some concluding thoughts or anything. I'll start with you, Mikey. Pick on you.
Yeah, I mean, so if you want to tell me that gravity is not a force, you have to tell me why it's different from the other forces. If you say geometry, other forces can be described with geometry. anything you can think of short of the fact that, gravity is special in the fact that it interacts with everything. And that's a very deep fact about gravity. And I think we should not mistake its universality, even though it makes it look different in a radical way. We shouldn't interpret that as it being characteristically different from the other forces. Full stop.
Yeah, and I would definitely agree with Mikey. So yeah, so I think this sort of pop science picture of this rubber sheet, and like you have planets curving the rubber sheet and things are moving along. Why I like it very much, that's a good geometric interpretation of this picture. I think it's way oversold, right? Like like sure, this is one way to describe things, but you can also use a very similar language to basically describe every other force, right?
Yeah.
So
they're like little twists in the rubber sheet, essentially, right?
Yeah, exactly. And I don't think we should use that to kind of emphasize the difference between gravity and everything else. We should use that to kind of celebrate the similarity and sort of in a magical way somehow. Yeah. In fact, Einstein's theory, I think it reinforces that, right? On surface, these forces feel different, but if you dig down into the math and in modern physics, they look more and more similar. Man, like these geometries, like it seems like they're just linked to each other, and I think this is telling us that the ultimate theory of nature will probably melt them all together, and it's silly to try to separate them, I think.
Wow. I'm excited. So we'll see them next year, right? Whether that's true.
That I'm not sure. I don't know.
Come on, Nima. You can do it.
Do we think? Yeah. Do we think we're gonna see it in our lifetime? I have high
I don't
hopes,
know.
but
I do.
yeah.
I'm more skeptical, but
Yeah. But I like
Yeah.
to think that there's this one force, this singular force that I guess if there's only one force, we might not even call that a force. It just is the thing.
The force.
We call it the force.
All right then. So with that, I'd like to thank everybody for joining us on this episode, and we'll see you all next week.
Yeah. Thank you guys for joining. See you guys.
Yep.
Bye-bye.
See ya.
Bye.
Bye.